grateful for them putting my talk just after Erica, because it's a very closely related topic, and you may appreciate the connection is very deep, but I'm hoping to give you actually a complementary perspective about what happens if do you have the phase resistance region, what are its properties. Of course, these beautiful pictures that come out of James Davis and Basov and many other people, they are we can learn a lot from them, but in many materials, it's very, very difficult to get accurate pictures, and there are many technical problems. It's actually very useful to have some other probe to really map the coexistence region and to see how big it is, where is it. And for this purpose, I would like to talk to you about a very recent work that is now just being considered for publication that has able to do this in one of those materials that Erica mentioned. These are Mott organics that Lee Millett and other people have studied in recent years, and where bulk dielectric measurements can actually be surprisingly informative about this interesting behavior. So, and I also like to thank the National Science Foundation for not dumping me after all these years, which is not trivial in this day and age. This work is done together with the experimental group of Martin Dressel. And there's a long list of people involved, which I didn't write here in the Dressel group, but the most important one is Andrei Pustogov, who is a former graduate student and now a postdoc at UCLA with Stuart Brown, a fantastic guy that's really was a driving force of almost all the experimental work. He's relentless and a fantastic physicist now on the job market. Samples come from John Schluter and some of the samples from Saito, who was with Dressel and now back to Japan. The theory component of the work, I'm a theorist, and the theory part of the work is done. The most important results are done by my current student, Yu-Ting Tan, who is an excellent student, wonderful physicist, and some previous work that also mentioned by Hanna Telecka, now professor in Tennessee, Miloš Radonjić, who is now assistant professor in Belgrade, and my longtime collaborator on Mott organics, Simone Frattini in Grenoble. So this is about metal to insulator transition. Eric already talked about it, but what I would like to focus on today is there is a class of materials and systems where you can tune yourself from a metal to an insulator without invoking any change of symmetry in the system. And this is very important because often symmetry of the crystal lattice, magnetic cord, and other things are making things very complicated, and then the results depend on the details of the symmetry. There are systems which can go from a metal to an insulator without changing the symmetry, and those are sometimes pure transitions. And there's a great deal of controversy what are the physical mechanisms behind this metal insulator transition. This is an important question that touches upon all the issues of strong correlation. Jan Zanen gave a beautiful overview yesterday and emphasized that in this regime where the metal and the nice Fermi liquid dies, something really strange happens. And so I'd like to take a look at that regime in a couple of systems. One of the systems that has been studied from the mid-90s is the 2D electron gas in semiconductors, where you can change the density and the Fermi energy and tune yourself from a nice metallic regime to the insulating regime. And oops, I don't see my mouse here. I don't know why. Anyway, so you can see the family of curves that are fanning out as you lower the temperature. Another class of systems that have been studied also a great deal are these Mott organics. These are molecular crystals where Mott transition is realized, and many of the experimental features look very much the same. You have the same similar family of curves, and both of the systems don't seem to show any change of symmetry on the two sides of the transition, no magnetic order, no charge order. These are systems where you have interactions presumably as a driving force for the metal insulator transition. So I'd like you to emphasize some details about this critical region or this transition region. You take a closer look at these curves, you will notice that there are actually resistivity maxima in both systems, and the temperature of these maxima seems to be coming down as you approach the transition. Finally, they disappear, and you have pure insulating behavior. One of the interesting questions is what is actually causing such a behavior in this regime? So you would like to know what are the physical mechanisms for that control transport. Is it something like coherence developing at low temperatures and nice quasi-particles, or is it phase separation? Those are very different scenarios, and this question, in fact, has a very long history. In the early days of correlated systems, Zach Fisk and other people discovered that in heavy fermions, there's a large drop of resistivity below the quantum temperature where heavy quasi-particles form, and this is called the coherence behavior, onset of behavior, you get a resistivity maximum. Similar things are seen in other correlated systems like Mott systems, and here's a theory plot from actually the MFT theory that shows you also how as quasi-particles form and you enter the Fermi-liquid regime, there is a resistivity maximum. Those are systems with negligible disorder and no homogeneity. On the other side, Elbio D'Agotto and his collaborators and many other people talked about systems which display phase separation between metallic and insulating puddles. And then as you vary temperature, in some cases, you can change the concentration of metallic puddles. And once they start connecting, just as Erica described, then we have metallic behavior. And that can give rise to a resistivity maxima as well. This sort of mechanism has been advocated for the 2D electron gas by Kivelson and Spivak, who speculated that when the Wigner crystal melts and then system becomes metallic at higher density, there could be some inhomogeneities forming, some phase separation bubbles and stripes, or some random patches forming. And then as you raise the temperature, you could change the concentration of the two species and again get a resistivity maximum. The last theoretical idea has been somewhat popular for a while, but actually is not really based on actual calculations as opposed to what, for example, Elbio has done. So there's a great deal of controversy in these systems. What causes this particular feature, which seems to dominate the transition region? Now, to try to answer this question in one system where we can provide an accurate answer, let's look at Mott organics. Those are molecular crystals, very soft. And what's spectacular about these systems is that they're extremely clean, but they also have a single electronic band near the Fermi energy, and other bands are completely out of range. And quantum chemistry and detailed studies demonstrated that these are essentially quasi-2D systems. These planes of conducting planes are essentially decoupled, and you can model them using a single band Hubbard model on a triangular lattice. So this is a very simple system, and you can tune it through a transition by applying pressure. Now, even though this is a relatively simple theoretical model that seems to apply here, there is a great deal of controversy associated with Hubbard model, and various physical mechanisms have been considered. Some people are very fond of spin correlations and spin liquid formation. They think that spin liquid type of physics dominate the entire transition region up to high temperature. And these ideas give rise to a phase diagram on the left, where you have an insulator or metal, depending on pressure. And then as you raise the temperature, you get into an intermediate quantum critical region which has weak temperature dependence. And this type of picture should give you a monotonic temperature dependence, metallic-like or insulating-like on the two sides, and a quantum critical scaling in the middle. These ideas have been motivated by somehow RVB type of thinking from high to C, but one can use these ideas also in these Mott organics. So Senthil has put forward a theoretical picture of this type. An alternative picture ignores the intersite long-range or short-range spin correlations, but focuses on how the localized spin, which you find in the insulator, can be screened on the metallic side by Kondo-like processes. And this type of physical picture, which is a rather local picture, gave rise to the so-called dynamical mean field theory. And it also gave a prediction about transition. So the phase diagram coming from DMFT, which sets aside intersite spin correlations, but emphasizes Kondo-like processes and the condensation into a Fermi liquid, gave rise to the phase diagram where you have a Fermi liquid at low temperature and high pressure, insulator at low pressure. There are two characteristic lines. There is a Fermi liquid line where the Fermi liquid dies, and a high temperature line, which is called Brinkman and Rice, which says that that's where the quasi-particles disappear, and that's where the resistivity maximum can be found. And then there's another line on the left, at high temperatures, which marks the closing of the thermal closing of the Mott gap, and that's where the critical region, the quantum critical region, should be centered. So those pictures are very different, and one important difference is that in the second picture, these two characteristic temperatures, they intersect at finite temperature and gives rise to phase coexistence region in the middle. So which one is right? Well, to try to address first the question, is there some kind of quantum critical regime or not? We studied the phase diagram starting from the DMFT perspective, and the phase diagram of DMFT for the Hubbard model is shown on the left. You have the coexistence region in the center, but the size of this coexistence region is extremely small. It's only about 1 or 2% of the bandwidth. So you have a broad range of temperatures. At high temperatures, you have a smooth crossover, and we found in this paper, we started this work about 10 years ago with my student at the time, Tanya Telecka. It's spectacular work, and she identified, in fact, very clear features of quantum criticality above the coexistence region at higher temperatures. So you get plots on the right side, you see the resistivity curves, and she identified the trajectory you have to follow to reveal the scaling, so-called quantum rhythm line. And this made a prediction for experiments. Experiments were done by Kanoda-san in Japan in the several years following our theory. And he repeated the analysis that we proposed. And he found in actually a number of materials exactly the type of scaling that we predicted with mirror symmetry of the resistivity curves, with critical exponents, which are very close to theoretical ones, and strange exponential behavior of resistivity describing the scaling curve. So the scaling in the high temperature regime has been confirmed. It seems to be very robust, very universal, and it follows the detailed shapes predicted by theory. So that's nice, but you would like to know more. You would like to know how universal is this structure of the phase diagram. How about these characteristic crossover scales describing the thermal destruction of the Mott insulator or metal? You would like to map them out, and this is where I got connected with Martin Dressel's group through Simone Frattini, my long-term collaborator, and we struggled together to actually try to map the entire phase diagram, all the crossover regions, using optical conductivity. And this was done. The optical conductivity of an insulator, Mott insulator, is shown on the top right. You see how the gap forms. And then from the shape of this Hubbard band, you can extract the interaction energy U, shown in these little panels, and as well as the bandwidth. And you can then map this on the phase diagram, shown on the left. But you can also find the so-called Wigum line, quantum Wigum line, which is the boundary of the Mott insulator, which is marked by the fact that as you sweep the temperature or the pressure, there is a large resistivity drops as you depart from the Mott insulator to metal. So this is the quantum Wigum line. This is the center of the critical region that Kanoda-san explored. And we found that as we properly rescale the interactions and the bandwidth for different materials, then the location of this crossover line is exactly universal for several materials of this class which don't display any magnetic order. So this was published in Nature Materials a couple of years ago, and gives you a very good confidence in that this phenomenon is rather robust and rather universal. So now what I'm showing you here is how the Mott insulator is destroyed by raising temperature or increasing pressure. But we can ask what happens more on the metallic side, and you can get a glimpse of this by actually looking at transport properties. And so in the top left panel, you can see the resistivity curves that I've shown in the beginning, and you see that at low pressure, you have insulator, resistivity is shooting up on a log scale, but then on the metallic side, it tends to turn down at low temperature and display metallic behavior. So here's the you see the family of resistivity curves here. I should note that these resistivity maxima that are seen in the experiment are also displayed in the simple theory for the clean Hubbard model, and you can see these resistivity curves showing the maxima on the metallic side of the transition, and this is well on the outside the phase coexistence region. Now, the theory says that there should be a phase coexistence region, but if you take a look at the resistivity curves, or the contour plots, the color-coded contour plots of the resistivity, you can identify several crossover lines. We can see by the inflection point of the resistivity on the log scale versus pressure gives you this quantum rhythm line where the Mott gap is closed and the resistivity gradually drops. You can also see the destruction of quasi-particles as a resistivity maximum. This is a so-called Brinkman-Rice line, and the Fermi liquid line where we depart from the Fermi liquid behavior at low temperature displaying T-square resistivity scaling. So all these crossover lines are seen, they are consistent with the theory. However, we don't see any clear evidence of the phase coexistence region. If you look at resistivity, it's difficult to convince yourself that in fact there is a phase coexistence region which is well pronounced and significant. And in fact, Kanoda-san has published recently a Nature Communication paper claiming that this is a quasi-continuous transition and advocating another point of view that's different than what the DMFT picture suggests. So basically neglecting the phase coexistence region and phase separation. So there's a great deal of controversy here. Normally people do reveal the phase coexistence region by hysteresis, but this, for technical reasons, is very difficult to do in these systems because of cryogenic problems in the Kelvin range. Notice that this phase coexistence, if it is there, should be existed below 20 Kelvin, where it's difficult to do cryogenic experiments. So we have technical problems in revealing phase coexistence if there is one. So to this end, the Dressel group has decided, together with the theory backing that we have provided, to look at this from a different perspective and to go to much lower frequencies in the dielectric range of the order of, say, 50 kilohertz. So this is basically almost the DC limit, and measure the dielectric constant, which is the real part of the electric constant, and map its behavior across the entire phase diagram. And now suddenly you see a completely different picture, which is extremely appealing and very telling about what happens in the system. So we generally expect the electric constant to be positive in the insulator and not very large. On the metallic side, we expect the electric constant to be negative and large in magnitude, and then a gradual crossover from one to the other. So indeed, this is at high temperature what you see. You see, this is color coded. We see in the Mott insulator, the electric constant is of order 10, which is what you generally expect for insulators. And then as we raise the temperature and or pressure, we depart from this region, and in the high pressure side, low temperatures, you see it's color coded blue, rather large in negative values for the dielectric constant, indicating a metal. What I'd like to point out is that what is really remarkable is how accurately the quantum rhythm line, which was determined by transport, is actually matches the color code of the dielectric behavior, where the dielectric constant is essentially constant in the entire Mott insulating regime up to the rhythm line. And on the metallic side, you see the blue shaded region, which is negative values of the electric constant, kicking in not at the boundary of the Fermi liquid regime, but at higher temperatures where the resistivity has maxima, and optics shows that the Drude peak is destroyed. So this is the Brinkman-Rice line, where the quasi-particle is thermally destroyed, and it displays beautiful dielectric behavior. So dielectric behavior directly tells you where the quasi-particles are dying. Somewhat higher, note this is the log scale, temperatures somewhat higher, much higher than the Fermi liquid boundary. What is most remarkable in these experiments is that at low temperature, suddenly you see yet another region forming in the middle with a very deep red color and not the log scale. You see the dielectric constant shooting up to values something like 5,000 or 50,000, depending on temperature, gigantic maximum of the dielectric constant, which is completely flat in the insulator. And then only in this intermediate regime, it has an enormous enhancement, which clearly maps very well the phase coexistence region. And this phase diagram, it looks exactly like what the DMFT theory has predicted. Now, I would like to say a few words before I end about what the theory means. But before you do that, let me just show you this very pretty phase diagram. And on this 3D plot, you see how, as you lower the temperature at high pressures and the quasi-particle forms, there is literally a cliff. It's like a cliff that you drop into, so you can really see a very dramatic mapping of different dynamical regimes here on the 3D plot as well. Now let me go back to simple theory. So what we have done to try to understand this is to use the DMFT to calculate the transport and optical properties of the two phases. So outside the phase coexistence region, our result is just the result for the clean Hubbard model. But in the phase coexistence region, we assume that you have volume fractions changing gradually. And then we have to set up a random resistor network where the two species are, they have resistivities and the electric constants corresponding to the two phases. And we vary gradually the volume fraction of the two phases. This is what we have done, and the result is shown on the right. You see these color-coded plots, they exactly reproduce the experimental behavior, and we see a huge dielectric enhancement only in the transition region. So this inset on the left bottom, you see actually, this is a crosscut. The red curve is the dielectric constant of an insulator, which is pretty much constant and featureless. The metal is negative and large, and only in the case of phase coexistence and an inhomogeneous region, we find a large enhancement, which can be as large as tens of thousands. It's a huge dielectric anomaly only in the presence of inhomogeneity. So this is what the theory gives you, and it is, in fact, this effect has been known within percolation theory. And let me explain its physics very quickly. Simply, if you have resistors, for example, shown here in series, describing the connecting metallic clusters, insulating clusters, you can polarize the insulator and you get a modest polarization in the insulator. But if you replace some capacitor with a resistor, so to mimic a metallic region forming in the middle, then there is a larger region that can be polarized. So you gain a larger dipole moment and a larger polarizability so that the electric constant can be enhanced. If these metallic regions start connecting, then the current will start flowing and you lose your polarization. So this clearly explains that you need large and disconnected metallic clusters in the dielectric, in the phase coexistence region to get this large anomaly. And this is what this very simple theory actually predicts. So I'm not going to give you many more details of this calculation, which is rather straightforward. It took quite a bit of effort from UT to computationally calculate the dielectric properties across the entire DMFT phase diagram and to use it within percolation theory. So this was done quantitatively and it matches the experiment very nicely. But let me now just end with a few comments. So what I tried to convince you is that in addition to mapping through optics or STM, which is probably the best way to get an insight into phase coexistence and in homogeneous regimes, you can also use a bulk probe like the dielectric spectroscopy to really very vividly map not only the phase coexistence region, but also various dynamical crossovers. So not only we see a huge enhancement of the dielectric constant, you can appreciate this even better if you look at the inset on the phase diagram. You see the electric constant has a gigantic red peak in the middle, mapping exactly where phase coexistence is. But it also marks the boundaries between the Mott insulating phase and the incoherent conductor at high temperature, and also on the metallic side, the boundary where the quasi-particles vanish and you turn into an incoherent conductor. So this is a very, very nice and useful probe, which has not been really appreciated so far. Of course, we would also like to combine this with imaging. In fact, I'm proud to say that in Florida, we hired Won Shin Ni, who is until now was a postdoc with Basov, and we are hoping to use his near-field camera to combine this with this dielectric type of measurement and to gain really a better insight into what really happens. There's a lot that can be done in the future, and one particular direction that is now already underway by Kanoda-san and also by Dressel's group is to actually introduce on top of phase separation disorder and to increase it further and further. What Erica mentioned, discussed a little bit the effect of disorder. What we expect is that when the disorder is not present, then one phase or the other will win. like in a liquid and gas transition in the glass. To get domains, we need some weak disorder, and if the disorder is weak, we will get relatively large domains with modest domain walls. But when we put more and more disorder, eventually the phase coexistence region will be completely destroyed, and then you won't be able to talk about two species or two domains. How this exactly happens is a subject of current work. Kanoda-san already has 2 papers published, one PhD, one PRL, showing how the phase coexistence region can shrink. The TC, the endpoint, can be pushed to 0, and then one can study this 0 temperature quantum critical point in greater detail. He claimed that the quantum critical scaling that we proposed and he found at higher temperature in clean systems now extends to lower temperatures, and he calls this regime the quantum Griffiths phase regime, which we discussed in early work, but there were no experiments to show them. What will be even more exciting, or equally exciting, is to use these ideas in other systems like the 2D electron gas, where to this moment there is a great deal of controversy whether phase separation or Mott-like physics dominates the metal insulator transition. And of course, there are many, many other interesting things also that one can study and one can hope to study in this context, such as dynamical behavior, non-equilibrium behavior, noise spectroscopy, and in fact, Dressel has tried to recruit my Dragana Popovic, my wife, who is an expert in noise spectroscopy, to actually study now this dynamical behavior in this highly non-equilibrium system stuck between the metal and an insulator. So I'll stop right here. Thank you very much, and I'm happy